Okay, I'm officially recording, and let me also share a screen from my. Okay, let me start. Okay, can you see the screen?
Yes.
Okay, thank you. Yeah, I wanna just yeah, we also we derived a formula and we solved some short problems. And let me start to write the actual problems, long problems to cover everything. And also, yeah, we talk about item by item how to find the stress, compressive stress and tensile stress in the beam, right? Under the moment, right? So we already have the formula and we already know how to find the moment of the inertia, but now let's cover all of them in the one actual problem, right? So let's assume we have a beam. We have a beam. For example, this one. It's 20 kips, 20 kilopounds. And let's see, I want to find this, maybe in the middle. Let's just put 10 feet here. And this is a section AA, right? We want to find the maximum compressive and tensile stresses in the section AA. Okay, in this sections we wanna so this is a symmetric beam, therefore the reactions also would be 20 kips each one, right? You can use the summation of force in direction of y, take the moment, but since the is very symmetric, so we have the same reactions, right? 20 kips. Okay. Now let's focus on the section AA. Now statics. So statics. We're gonna find the moment. Free body diagram. Okay, this is the 20 kips. This is 20 kips. Let's this is a 10 feet, this is 10 feet. In this section, section A, we want to find the moments, right? Because we want to find the stress space at the moment. So let's, for example, if this is the point A, right? Here is, for example, point A. And the summation of the moment, let's about point A is 0. We have, let's fit this direction, for example, then we have negative, and then moment minus, that's 20 times 2 in the opposite directions, right? What is the unit of the moment? 200. What should I write? Anybody? One? Can you hear me? Just as
Yeah, I can hear you.
so the unit of the moment is
Kilopound.
kilopound feet. Okay. So that's a moment. We need that. So okay, so let's just further. If you need, yeah, if you don't remember, so for the stress in the beam based on the moment we have, we derive these equations, right? So to find the stress, we need the moment. So we find the moment from the statics, free body diagram equilibrium, and also we need to find the moment of the inertia I, right? And C, we want to C is a point to the natural axis, right? So we want to talk about C later. So okay, here the other things, M, when we apply the M, if you remember, we discussed the top based on this direction of it under compression, the bottom under the tension. This is another thing also we need to talk. We need to talk once we wanna find the stresses, right? So the first step, we find the moment. The second step, let's find the moment of the inertia. Moment of the inertia is depends to the section. This, which means we need the section of this problem. So cross section. So the cross section for this beam is given. This cross section is beam is given. So let me draw the beam cross section. Let me draw that. So which means cross section, if you look at the beam from this view, what should we see? So this is the given. It's a T shape. It's a T shape. Let's see. We have a cross section, something like that. And you have this one. I think we did some quiz similar to this one, right? Okay. So this is 1 inch. This is 10 inch. This one is 0.5 inch, and this dimension, yeah, the dimension of this would be 20 inch. Okay. Let me write nicely. This would be 20 inch. Okay. So we know. So what's the first step if you wanna find the moment of the inertia? Before moment of the inertia, what do we need to find?
Find the
Center point.
the centroid.
Center, exactly. Find the center. Thank you. So so we know center is somewhere, but we don't know the exact number. So let's first figure.
Quick question, sorry. The center, do we need to just do like a Y or X or both, or?
Here is the moment of the inertia in direction of X in this direction, because you know because the moment is the direction is outside the plane, right? The outside the plane, and then which means we want a moment of the inertia in this directions, right? X, for example. It depends. If we define the direction outside the plane X, then this one would be this directions would be X, right? Yeah, but we want to talk about directions more details once we talk about both moments, moment in direction of X, moment in direction of Y, and then we said, okay, we need IX, we need IY, but right now, just this direction is in this direction of the moment, right? That direction is the direction of the moment, because this direction is exactly the direction of the moment, right? Direction of the moment is the clock. It is outside the paper, right? And if you look at this view, then we have that direction. Does it make sense to
you? Kind of. I'm still trying to wrap around how you determined that it was around the x-axis.
Yeah, I wanna just solve.
I don't know if I missed it or.
Yeah, let me. Yeah, the direction of the moment. So the moment of the inertia. Yeah, once we talk about the moment of the inertia at the beginning, once we derive the formula, once we derive, we have integral y squared dA. If you remember that one, then the moment of the inertia is in the direction of m. For example, here, if the m in direction of, for example, x, then okay, we need ix. If we ask if m is direction of z, we need to I z. If direction of the m in direction of y, we need to I y, right? So now the direction of the the direction of the moment here is out of the plane, right? And if you look at this one, for example, this one would be the direction of the moment is somewhere here.
Oh,
Right?
so on top, is that a top view of the object, or we have the moment of inertia? Is that the top view? Yeah, that's
This one,
20K.
20K is upward, right?
Yeah, no,
Yeah, 20K is this in direction of, let's see, for example, let's write like that. If this direction is z, this direction of y, okay, moment is in direction of x.
oh, okay. So it's
Okay.
a view from the top, right?
Yeah, yeah. If direction of z, this direction of y, moment in direction of x, therefore here, moment is in this direction, in the horizontal directions, right? Maybe somewhere here, if the center here, this is x direction, right? So, which means this would be y direction, this would be x direction, and z direction here would be in the perpendicular dot. And here we can see that this z direction. Does it make sense to
Okay.
you?
Yeah, yeah. I just had a hard time visualizing it.
Okay. Okay, now, so okay. Let's find the center. For the center, we said, okay, we should fix the axis. Let me fix this axis. So we can fix top or bottom. So we fix this one. And let's find, so we have two things. Let's, for example, this one, A1, and this is A2. Then Y bar would be, YA plus Y2A2 divided by A1 plus A2. Okay, and now let's just help me to write. Respect to this line, what is, okay, this is the center of this. This is the center of that. What is Y1?
20.55.
Yeah, is it this 0.5 inch, right? A1 is 10 times 1, right? What is Y2? Y2 is, say that again?
10.
10.
10 to this is half of that. And respect to this line is 11, right? Just respect to time, because we want to find based on fixed line. 11 times.
Are you doing it from the top?
Yeah. I'm doing from the top.
Okay.
Yeah, for this problem, something different. I want to just. Yeah, from the top. Right? So.
Excuse me, Professor, is that should be 10.5, not 11?
Hmm?
Yeah, I think that's, and also 28 and 20.
No, this is 20.
Yeah, but okay. Yeah, I thought that was 28.
This is 20. This is the Y bar from the top, right? For example, now you have Y bar here, and this one would be 5.75 inch. Okay.
Where did you get the 11 from again?
11. The half of this is 10, right? Because this is 10 plus 1 inch.
Wouldn't be plus half of that 1 inch thickness?
Which value you are talking?
The horizontal top bar, it's 1 inch thick, right?
Yeah, is it 1 inch? Half means because this center to this line is half inch, right? This
Yeah, so
half.
technically from all the way from the bottom to all the way to the top, it's going to be 21, right? And if you have that, it's going to be 10.5 now.
From bottom, you said?
Yeah, all the way from the bottom.
Yeah, yeah.
All the way
you
to the
got from
top, it's
bottom.
21.
Yeah,
10.5. Not 11 should be, I think.
11 is okay. Half of that is 10 inch. Okay,
Yes.
10 inch plus 1 inch is 11.
We're not doing half of the thickness of the top bar, right?
No,
We're
no, no.
doing the full thickness of
Because
the
we
top
need
bar.
we need to this line. This is a fixed line.
Oh, okay.
This is a line, fixed line. We should measure from the fixed line.
So you're measuring to the middle of this, the second bar, right?
Yeah. No, measuring this line. This line is the top.
Right.
So full top line and half of the vertical line.
Yeah. Yeah. So measure from a fixed line. Look at this fixed line, this red line. Okay, this Y1 is center of these to that is ½ inch. For the second one, center of these to the line would be 10 plus 1 is 11. Right?
Yeah.
Okay. Okay, thank you. So 5, so then if you use a calculator, just this fraction, Y bar would be 5.75 inch, okay? So that's Y bar, and then let's formula for the moment of the inertia, okay? I would be I1, for each one, let me write. If you remember, formula would be BH cube over 12 plus AD2. This is for 1. BH cube over 12 plus 82 for the second object. Let's write. Just help me. What is for the first one? What is B? What is H? For the what is B? B is 10, right? 10 times H is 1. A is 10 times 1. What is, okay, D is the difference between the center of the object to center of that part to center the whole center, right? So we need to find this distance, right? Distance between two, right? That would be 575 minus ½ inch, right? That's the distance between this red one is the distance of the shape. This one is distance of the area of one. So this distance, the difference is the 5.75 minus 5, right?
Was the 5.75 given, or did we
No.
found it?
I found based on this formula.
I'm sorry, I don't see a cursor.
I found based on this formula.
We got it from the Y bar.
From
Oh,
here.
okay.
From Y bar.
Got it. Thank you.
Okay, oh, sorry, I should. Oh, you cannot see the cursor now?
No, it's
okay,
can see
okay,
on
okay.
the screen.
Okay, I will show you the pen.
Yeah, that's why when you're saying like from this point, it's kind of a little confusing.
Oh, okay, sorry. So okay, I want to show based on the with the pen. Okay, because I use the two devices. Okay, let's plus BH cube over 12 for the second area. What is B for the second area? This one is the B. The
0.5.
0.5, right? Thank you. 0.5. What is H?
20.
20.
I'm sorry, the B was provided, right? Or the B
Yeah.
value?
Yeah, this is the B. This is the B.
Oh, okay, got it.
Okay, plus A is the 20 times 0.5. And the distance now is, we need this distance, the difference between the area, the area of the center of the shape, the whole shape, and the center of the second one, right? So how can we find this one? What do you think? We can-
11 minus 5.75.
Right, 11 minus 5.75. Thank you.
Does it matter which one we do first? I
It
mean,
doesn't
I know
matter
we're gonna get a
because-
positive,
It
but
doesn't matter because we use a square.
okay.
So again, this distance, the distance here would be, we can use this distance is 11 minus this distance. This is 11 and this is 5.75. Then we can find the difference. That's D, right? Okay, so I would be the answer 885. What is the unit? Be, if you remember, inch to the 4, right? So, okay, now let me, so we'll find that one. So let's review the formula. Formula would be MC over I. We find M, we find I. Okay, now it's almost, we are very close to find the hysteresis, but let me, to find the hysteresis, if you remember, let me draw this. Okay, let me draw this part in the large scale, draw this part in the large scale. Then, okay, if we have this part in the largest scale, we have a moment here, okay? So the cross sections, we have 5.75, right? The Y bar. Let's look like this, right? It's the neutral axis. 5, so let me write with the color. This is the 5.75, you find it, right? It's a Y bar, okay? And can you tell me what is this distance? It would be
Would it be 21
15.25.
minus
21.
5.75?
Yeah.
the 20 plus 1 is 21 minus 5.75. This would be 15.25,
15.25.
right? Okay. And
Okay, so we're looking at it as the solid object, right? More or less.
yeah,
By the drawing.
yeah. So now, okay, as we said before, with this moment, the top is under compression, right? If you remember the lectures before, and no, it should be 15 plus 25 because the total length would be 21, 20 plus 1 inch, right? And this is tensile.
What does the NA stand for?
Natural axis,
Neutral axis. Okay.
neutral axis, the axis from the center, right?
Yeah, that makes sense.
Yeah, if you remember, we discussed about the neutral axis. That's the point. If you remember, there is no stress on that, right? Because here, because the formula MC over I or sigma my over I, if you remember, we discussed once we increase the y, we have a stress. But if your y is 0, then there is no stress. So because of that one, we call neutral axis. Okay.
Yeah. Thank you.
Okay. Now so the top is compression, the compression, and the bottom is under tensile. So which means if we apply this moment, if the deformation shape would be something like that, right? It looks like this is compression, this is tension. Okay, so in this case now, okay, let's back to the problem. It asks find the maximum compressive max and tensile in this section AA. So look at the formula to find the maximum compressive. So we have M, we have I. M and I is now constant. Okay, to find the maximum compression, so we need to use this length. We need to use Y equal this, right? Right? Let's put, for example, CC. To find the maximum tensile, this point is the makes the maximum tensile because this is the last point. This is an H point, right? Maybe we define this as CT, right? If we pick another point here, for example, this point. So, but this value is less than CT, right? This value is less than CT, then in this formula, sigma will not be maximum, right? So once you are asked to find the maximum, just put the point in the edge, right? Then find the distance of that. So here, top is compression, bottom in tension. So sigma. So for the let's write for the compression. For the compression, sigma max would be, what is M? M is 20 Gibbs feet. So be careful. Since this value CT based on inch, let's change Gibbs feet based on Gibbs inch. Just multiply 12, right? This 12 means feet to inch. Okay, and C is the 5.75 divided, what is I? I is 8.85. Okay, this is sigma max compressive, so the answer would be 15.59. Okay, guys, what is the unit?
KSI.
Feet per inches squared.
Yeah, KSI, Gibbs per inches square, exactly.
Pounds, I mean.
Yeah, kilopound. So for the tensile, sigma max would be again 200 times 12. So now this distance is 1525 divided by 885. The answer would be, the answer I have is 41.36 KSI. So in these sections, the maximum compressive stress is 15.59. The maximum tensile stress is 41.36. Okay, so again, we use this formula we use my over I, this formula, and just the first step, we find the moment from the statics, then I from the cross section, and then just look at the the problem. It asks the maximum, so this is the top. Yeah, here based on the direction of the moment, the top in the compressive compression, the bottom in the tension, and then just we put the distance, the appropriate distance, and find the maximum hysteresis, right? Does it make sense to you?
Yes, it makes sense.
Okay. Yeah. Yeah, this is all the procedure we need to, this is for the find the stress based on the moments, right? We have, what's that? We have a beam at one section, find the moment of the inertia, and then these steps. So, but now the question is, okay, we derived the formula, we solved the problems based on the only one material, right? So the cross section here, we don't know, maybe is it steel, maybe wood, but the cross section, once we derive the formula, is based on just one cross section. And another interesting topic is what happens if the cross section is maybe composite one, is maybe it includes both steel and wood. If you remember, for example, it's in many members, right? Especially if the people in the civil engineering, the concrete has also in the concrete and steel, right? We don't want to cover that one, but those problems, but want to cover if very simple things. If some rectangular things include both things, steel and wood, for example, something like that, right? So now beam, let's, for example, beams of different material. So let's write the problems and then say how can we solve. Okay, already we derived the formula based on one material. We can know the material based on the elasticity of modulus, right? Or Young's modulus. So, and the stress strain based on the one material. But now let's look at if you have the cross section something like this. If you have a cross section, for example, something like that. This is rectangular, and also we have maybe one is here. Let me write with the dimension. Just assume we have this one, okay, and then this is also 10 millimeter, and this is 75 millimeter. And okay, this one, for example, wood, elasticity of modulus of the wood is 1.5 times 10 to the 6 psi. And let's assume this one is, for example, steel. All right. Steel, elasticity of modulus is still very strong, right? Okay, so the question is now, so we need first to modify the formulation before solving the, so the general formula is, okay, sigma equal mc over I, right? But now we need to, that formula actually obtained based on one material, which means I is the moment of the inertia of the maybe just one material, is steel or wood. Okay, but now we have the two things. So let's okay, let's focus on this point A, right? This point is in the both steel and wood, right? So if you're okay, which means this point has a set, the deflection of this point A. If the cross section is under the moment, the deflection of that, it could be, we can define this one deflection of the both steel and wood, right? Because exactly at the line include steel and wood, right? Which means at point A, the deflection or strain is delta over L, right? If you remember the formula. Strain for the both steel and wood at point A, only at point A, it would be equal, right? Strain for steel and as W at point A is the equal, right? Okay, what's strain are equal? So do you remember what's the relation between strain and stress? Sigma is E epsilon, right? Stress strain relationship we defined long time ago. So which means the strain would be sigma over E, right? Sigma S for E, sigma S for ES divided by ES equal sigma E, sigma wood divided by E wood. So, okay, this is one thing. So let's just leave this one. So we need this one. We want to use this one later. Okay, but the only things we know at point 8 is a common point between steel and wood, which means when we set the strain or deflection at point A, that could be for both material, steel and wood. Okay, let's just leave this one. The other things now, okay. In this once we have a composite sections, we need to find the equivalent material, which means we pick one material. Okay, we have wood here and steel. We have wood here and steel in the bottom. So we can, I want to pick a steel, and instead of a steel, put the equivalent wood. Okay, that's the idea for that. And how can we find the equivalent wood instead of steel? Okay, so but we know this is the area of the steel. Okay, in this area we have a stress, applied stress, and we know stress on this area, stress times area would be the force. And then if we wanna remove this steel and put the equivalent wood, the force on that would be the same. It must be the same, right? Because equilibrium. So if we, which means if we remove this steel and put the, instead put the wood, the force on that would be the same, right? The force on that because of the equilibrium. So the P of the steel must be the same as the P of the wood, right? That, so now I'm starting the step to find the equivalent wood instead of steel. So I wanna just temporarily remove the steel and put the wood to make the consistent material, just the cross section only based on the wood, right? And at the end of the problem, then we come back to see the effect of the steel. Okay, so P of steel, we know P of the steel is AS sigma S, right? Because sigma, if you remember, is P divided by A, therefore P is sigma times A. Okay, the same A of the W would be sigma of the sigma of W. Okay, the other things now, okay, now look at this equation. In this equation now, we can, instead of stress of steel, write everything based on the wood. So now let's modify this formula AS, and instead of sigma S, write ES over EW sigma W. Do you agree with me? Because here I'm using star, using this equation, and instead of sigma S, I put ES EW sigma W. Okay, do you agree with me?
Yes.
Okay, and now we can, in this equation, we can just cancel sigma W. Okay, so let's now denote AW. So we have area AW is NW, NAS. Or let me write like this. Let me, maybe it's confusing if I, okay, let me write one more steps. Let's write like that, ES, EW, okay? Equal AW over AS, right? This is the one step. Do you agree with me? This is it. So, okay, look at this equation. We know the material, we know the steel and wood, which means we know the elasticity of modulus, right? Elasticity of modulus for each one is given. ES, we know the ES, EW, EW, ES. So then ES and this fraction, ES and EW, ES over EW is, which means is given. So let's define ES over EW as, for example, N, right? N. Therefore, N would be equal AWAS, which means AW would be NAS, right? So it's very interesting now. Because, okay, we have ESEW, we can find N. Since we have N, now we have area of the steel here, right? This is area of the steel, AS. So area of a steel, you can, because we have a dimension. So, and we have N, so we can find the equivalent wood for that. So let me now draw a figure and remove the steel in the bottom and add the wood, right? So let's just okay, let's find N, right? What is N? N is ES over EW, right? Is N ES over EW. What is ES? ES is what is EW? So what is N? This is cancel. 30 over 1.5 is 20, right? So, okay, now it's very interesting. So if in this steel, if you multiply 75 millimeter by 20, then we have the equivalent area for the wood, right? Because this area, this is area of the steel. We fixed, we don't change the depth. We keep 10 millimeter because we want to find the stress in the depth, right? We find the stress in top, bottom. So we keep this one as a constant. Then we just change the wide. We change it, so which means we need to multiply this one wide to 20. We can find the wide of the equivalent wood. So let me draw the figure again. This is the original wood. Let me write based on the meter, 0.15 meter. This is 0.3 meter. And now equivalent wood we have, and I just remove that steel, but I keep the thickness as the same. But here that would be, what is N? N is 20 times 0.005. 0.005 is a dimension of the steel, right? I just multiply it to 20 to make the area 20 times on there, right?
But then if you only multiply by one dimension, that wouldn't be an area, because area is base times height. So that doesn't make sense to me.
Yeah, let's say something to you. For example, this is A, this is B, right? Area is AB, right?
Yeah.
We want to find 20 times of that. So just pick one dimension. Pick one dimension. This is N. Then NA times B. So this is A1, right? The A2, NAB, and then would be, what is AB is A. Is N times A1, right? If you multiply both dimensions, we have N square. It doesn't make sense, right? Because we have AW N times AS, right? Right? AW is N times AS, right? Does it make sense?
Yeah. No, I mean, no, it still doesn't, because area would be the base times the height. So why are we only multiplying it by the base and not the height?
We can't. You said both. We should multiply both.
Because isn't that what the area is? The area of the steel would be the 0.1 times the 0.075.
Yeah, 0.1 is this one,
So basically, are you just trying to stretch the steel or?
Yeah. I wanna stretch a steel and instead of a steel put the wood. Now this is wood because I wanna use the one material. This is wood, right?
Okay.
Right.
So basically, you just found a relation.
Relation, but it should be n times that because we find because AW must be NAS, right?
Mm-hmm.
To find the NAS, just we need to multiply one dimension by n, but I pick the width, not depth, because because I want to fix the depth, because I find the stress, because I want to find the stress in the bottom or top. We cannot change the depth of the sections, right? Okay.
And
But
for this figure, is our reference the bottom of the steel bar? Like it's the very bottom? Is that where you put the reference?
yeah, exactly. Okay. Yeah, I keep the dimension for the 10 millimeter. I keep here this 10 millimeter. I just wrote based on meter, right? But I increase the y, right? Now does it make sense to you?
Yeah.
Okay. So again, once you wanna find the area n times the the new area base n times the before, just multiply one side to n. But here we need to multiply just the y because I want to keep the depth because I want to find the stress on that. So okay, now that's a new figure, right? So this is a new figure based on both is wood. Okay, let me now find. Okay, let's review again the formula. We need to solve this one, find the stress. So m in this problem, m also given. M is given. Let me write here. M is 25.9 kilonewton meter. Okay, please write this one. 25.9 kilonewton meter is m. Okay. And now it's good. Everything based on one material. So let's focus on that to find I. What is the first step?
Y bar.
Y bar. So let's denote this is, for example, A1. Y denote this is A2. The bottom, you said, no, it should, no, that's a 10. 10 millimeter, yeah, 10 millimeter divided by 1000. Yes, you are right. I miss, yeah. Thank you. It's very, yeah. 0.01 meter. Thanks.
So are we basically giving the steel like wood properties in order to solve for the problem?
Right, exactly.
Okay.
This is A1, this is A2. Let's Y bar. Let's Y bar A1 plus Y2 A2. Now it's a step I need your help.
Is area 2 steel or wood?
Both area as wood. Here the original area is steel here, right? But I find the equivalent area based on wood here. Okay, now it's wood. Okay,
Yeah.
Okay, let's now to find the center, let's fix one. Let's make an axis again based on, yeah, let's just pick, this is a fixed axis. I want to find, okay, the center of this here, the center of this here, and then we want to find the center, the Y bar. Okay, now let's just help me to write. What is Y1 respect to that's red axis?
0.15.
0.15. times what is A1? Do you agree with me?
I agree.
Thank you. Okay, what is Y2?
0.35.
Yeah, 0.3 for Y2 would be, let me with the other color. Y2 would be from here. 0.3 plus half of this, half of 0.001 divided by 2, right? Therefore, okay, I want to also write with the green to distinguish. So would be 0.305. Okay. What is the area of that? A2?
0.01 times 1.5.
Yeah, thank you. A1 is, then let's copy from the numerator. Okay, that's okay, and then we can find the Y bar if you use a calculator. We have,
Wasn't the bottom base 1.5?
say that again.
The base for A2, isn't it 1.5?
Base.
You have 0.15.
Here is 1 point.
Yeah, you wrote 0.015 times 0.01.
Yes, thank you. The problem is this number is very similar to each other. Thank you for your correction. Yeah, the things is yeah, my note is okay, but I'm looking for the figure, and then these numbers is very similar. Okay, thanks. Okay, now it's Y bar. Now we have Y bar. What's okay? Y bar is fine. Y bar, which means, let me show with the other color. Y bar, for example, it's maybe here. It's Y bar. Okay. We find Y bar 0.8. What is the next step? Next step?
Plug it in the find moment of inertia.
Moment of inertia. Thanks. I. For area 1. For area 2. Okay. Let's start from. What is the area 1? B is. Can you tell me to write?
0.15.
0.15. What is H?
0.3.
0.3. What is A?
Times 0.3.
Yeah. Now D from the to D, we need this distance, right?
Yeah, so 0.3 minus 0.188.
This would be.
What's the center minus that?
Yeah, 0.8. Yeah, it would be 0.15 minus 0.1880, right? We need, let me write. So to find this, we need this distance minus this distance, right? Do you agree?
Yeah.
So 0.1880 minus 0.15, okay? let's fit this color. Then if you this is for now, let's for the second. What is so area 2? What is B?
1.5.
What is H? Do you agree?
0.01.
Mm-hmm. What is A? Okay, now let's find B. That's it's very important. That's maybe that's. So for D, let me use with the other color. We need now this distance, which means we need. Sorry, I did something wrong. We need the. We need this distance, right? Okay. So we can write what do you think? What should I write?
0.805 minus 1.88.
Yeah, we can. Yeah, for this red one, we can use this minus this. Please write with different color in your note to distinguish, right? So this large green would be 0.305, and this one would be 0.1888. Okay. I know it's confusing, but let me write with the green here also. If you back, then you can distinguish. Okay. The section in the book in chapter 4, maybe 4.4, I think. Okay. Now let's the answer. The answer would be 6.08 times 10 to the negative 4 meter to the 4. Okay. Now again, let's review the formula. Sigma is MCI, M is given, we found I. So now as everything is ready to find sigma, which means let me again I will look at the figure again, but since let me draw the figure. Okay. Okay. Let me draw first. Yeah, let me draw the figure. We find the moment of the inertia for this figure. Is good. Okay, and now I don't want to make it busy, just for the necessary items. So this is a sections and this is a moment on that. So the y bar, we find the y bar. Here, what is y bar is 0.1880, okay? Okay, this is the compression top, tension bottom. Okay, let's start this. So what is the, okay, if the formula is sigma my over I, y of the compression would be, or y of the compression or c of the compression would be this one, right? Would be, this is for c of the compression would be 0.1880, right? And for this c of t tension, sorry, just is because we want to find the maximum. This is the maximum for compression. In the bottom, the maximum here. CT would be 0.31 minus 0.88, right? Do you agree with me?
Yep.
Let's write for the compression first. Sigma max, M is given. Yeah, I wrote M 25.9. What is C would be 0.1880 divided by what's I? 6.08, 10 to the negative 4. Okay, guys, what is the unit?
Square inch.
Unit, you know, okay, moment is given based on kilonewton meter, right? Therefore,
Kilopascal.
how about this one? Kilonewton per meter square, right?
Yeah, that
Yeah,
one.
that's
Yeah. For tension, okay, let's find for tension, sigma max is 25.9. I didn't find this one. Just let me write like that. Max. But you can find with your calculator and this.
I got 0.1212 for that distance.
Yeah, it's okay. Would it be 5166? And now we have a very, very, very important additional step. Okay, sigma, okay, for the compression is good. For the tension, we find the stress for the equivalent wood, because this point, look at this point, this is location of the tension. Here is wood, but original figure is steel, right? And which means this point should be in the steel. Look at the original figure. Original figure is steel. Now we need to find the sigma of the steel. So how can we find it? Look at here. We have this equation, right? This equation we know sigma steel is sigma wood ES over EW. Okay. What is ES over EW? What's the parameter of that? ES over EW is N. N.
20.
Right, which means sigma for steel is N times sigma W. Now, okay, we find the sigma for W for the wood here. So therefore, sigma max in the steel would be N times sigma max for W, right? N is 20. 20 times 5166. That's the last things we should just don't forget this one. I saw that many people did everything right, but this is not much more calculation, but they forgot to just convert at the end, convert the wood again back to a steel, right? Because the original things is the steel, right? And we use this virtual section because with both steel and wood we are not able to solve that, because we derive the formula sigma my over I based on one material. Therefore we first temporarily we switch from we use equivalent to change the one material to the other material, use equivalent that material, and then but at the end we should check once we find the stress, if the stress in the area of the steel, then we should back and find it, and then based on this formula, right? this formula here, once we start in the start point, we know the sigma S is ES over EW times sigma W, and we ask for ES over EW as N. Okay? So, okay, guys, so that's the procedure to solve the composite section. So, in summary, we have only this equation. Okay? So, possible problem, if the beam is given with the load, we need to use the statics to find M. Because sometimes M is given. Sometimes maybe use the second, something like the second problem, M is given. That's fine. But if M is not given, the beam is given with the loading, use the statics to find moment. Okay? The second step to find I, and to find I, you should look at cross section also is given. Then you look at the I, the cross section. The first step is to find the center of the cross sections, Y bar. So, you know, as a summary, step 1 is M, to check M is given or not. If it's not given, use the statics to find one. Step 2, find the Y bar, because we need the Y bar. The step 3 is I. And step 4, just go back to the formula and just draw the figure again. Maybe again, draw the figure and just distinguish where is Y bar, something like that. And then if you ask the maximum, put this value, for example, I don't know, CC or CT, something like that, and then find the sigma, right? If we have a composite sections, we have one more step before that. In the composite, if you have a composite, we have one more step between step 1 and step 2. Let's write step, for example, 1.5, right? Then for sure, if the problem is based on composite, for sure the elasticity of modulus is given. Then find N also, maybe ES over EW or EW over ES. Right? Just convert one material to the other material. Okay, so if we have a composite, we have one additional steps here before going to Y bar. If not, that's right. So based on this, actually, I after the class, I wanna assign the homework, some problems for you, maybe 5 or 6 problems for you. It's cover everything from the stress based on the moment. That's a plan. That's for this topic. And the next things, the next topic, actually, somebody asked me, I think at the beginning, about the direction of the aim. So we said, okay, we have a one direction, but now we wanna talk about what happens if you have a two moment. One moment maybe in direction, one moment maybe in direction of X, the other in direction of Y. This is one case. The other case also, okay, we have the stress based on the moment. Also, if we have a axial force, because we have another stress also, right? The another stress is P over A, right? Based on axial force. This is based on axial force, right? And then this stress MCI based on the moment. What happens if you have both, right? How can we add it or subtract it, right? So this is a plan later. So, and also, so before going to both, so also I want to talk about what happens if you have both mx and my, and definitely we need to find both ix and iy. Why did you only multiply? Yeah, I multiply this one because the first one in the Wood region, because the first one is from this point in the Wood region, and because in the top here we have a Wood, right? And in the original figure, look at here is Wood, because this is Wood, right? We didn't touch this. But in the bottom, this point in the steel, right? And because here, yeah, there is, here we have in the steel, this point we use equivalent wood, right?
Is y the same thing as c?
What does that mean, C?
Where it's like the moment times c over I. At the bottom, you put the moment times y over I. Is that is y the same as c?
Yeah, C usually, yeah, sigma m over, okay, sigma my over I. If you have a sections, if you have a section like this, if this is a neutral axis, y could be any points, could be here, could be here, could be here, could be here, any point, could be y. Once I wrote C, the only difference C is the point in just these edges, just in the edges. This point I showed based is C, but this arbitrary point would be Y. If we want to find the stress at this point, maybe we said Y equal maybe 1 inch. If I want to find the stress at the edge, and instead of Y, I wrote C, which means the maximum Y, the Y max. C would be Y max. Does it make sense to you?
Yeah, thank you.
Yeah, the formula is the same. Okay. And so okay, so the plan for the next lecture, so I want to assign the homework, but the plan for the next week, I want to start from if you have two moments, moment in direction of x, y, and also what happened if you have also actual force, right? That's the plan for the next week. Do you have question about this topic? Or step 4? Step 4 is just find the stress. Step 4 is just find the stress, right? Just find, we have M, we have I, we put Y, and then find the stress. Yeah, you can redraw the figure, or if you don't want to redraw figure, maybe you can look at the figure back. It's not required to redraw, but I recommend to redraw without any additional dimension. Just put the Y bar and something like that, right?